Josh Bassett with how to write a retro arcade emulator.
Thanks a lot. Firstly, I just want to thank linux.conf for inviting me to give this talk, and to all of you folks for coming along this afternoon. So this talk is about a project I've been working on for the past 6 months or so. I've always been an inquisitive person, and I decided to write an emulator for one of my favorite games from the 1980s, just to learn how it worked. Before I embarked on this project, retro arcade hardware was something of a mystery to me. I had very little idea about what was actually happening inside one of these arcade machines I spent so much time playing as a kid. The best thing I discovered about them is that they are actually understandable. And that's to say, it's feasible for one person to learn about how they work top to bottom in a single human lifetime. I'm not kidding. If we stop and think about it, this is actually a rare thing nowadays. Modern computer hardware is notoriously complex. Today, it is very difficult to know how things work down to the chip level. But before we get into it, here's some fun facts about me. I work as an application engineer at The Conversation in Australia. If you don't already read The Conversation, I encourage you to check it out. It's got some great news and analysis from the academic community on all kinds of topics, like science, medicine, health, politics, all kinds of stuff. We're hiring, by the way, so come and talk to me later if you're interested in working for a not-for-profit, working with Ruby, JavaScript, and Linux. I've been a maker since I could hold the right end of a soldering iron, and writing code since the early days of 88.6 PCs. I pulled all of my toys apart as a kid, and it was quite a long time before I figured out how to put them back together again. This was a little project that I had from about a year ago, where I made a FPGA-powered LED matrix controller. When I'm not burning things with my soldering iron, I like to spend time in my studio writing music. This is a photo of my portable live rig, and I love modular synthesizers, so the thing in the middle there with all the wires hanging out of it is a modular synthesizer. If you want to hear what sorts of sounds come out of something like that, then most of my music's up on SoundCloud or Bandcamp under the moniker Seapelt. If there's time, I'll be answering questions at the end of the talk, but if you think of something later or you just want to reach out, then please feel free to contact me. Okay, so one of my favorite things to do as a kid in the 1980s was play arcade games. This photo is from a trip I took recently to Japan, and I checked out a whole bunch of arcades there. But I have very fond memories of the arcades in my hometown back in the 1980s and 90s. Even though my hometown only had about 20,000 people, there were quite a few dedicated video arcades. And there were arcade machines in every video shop, corner store, milk bar, pub in town. And I think it was my mum who introduced me to the arcades back in the day, but since those early days, I was hooked. One of my favorite arcade games of all time is called Rygar. It was originally built in 1986 by Tecmo, a Japanese video game company, and saw later releases on consoles like Nintendo Entertainment System, Sega Master System, Commodore 64, Atari Lynx, and others. This is the game that I built the emulator for, but the video you see here is from an FPGA version that I later built, and I'll talk more about that later. You may be able to spot that it had a few graphical bugs at this time to do with sprite priority. As with Rygar, popular arcade games were often ported to other platforms, like home computers and home game consoles. Another favorite game of mine from the era, 1984 actually, was Bomb Jack. Here you can see the difference between some of the major platforms. On the left side, we've got the original arcade version, which was running a Z80 microprocessor at 4 megahertz, and it had a whopping 8 kilobytes of RAM. In the center, we've got the Amstrad CPC version, which was also running a Z80 at 3.5 megahertz, and it had somewhere between 16 and 48 kilobytes of RAM, depending on which version of the machine you had. And then we've got the ZX Spectrum, which was running a Z80 at 4 megahertz with 64 kilobytes of RAM. So looking at these three images, I'm sure you can see a pretty striking difference between the different ports of the game. And the arcade version is pretty obviously graphically superior. Given that these were all 8-bit machines running almost identical hardware, why do we see such a massive difference in the quality of these different versions? To answer that question, we need to look at the differences between early arcade machines and home computers. As with modern computers, home computers of the 1980s had a CPU storage, so maybe a floppy drive. Some of them had cassette tape drives, maybe a hard drive. Input, so a keyboard, maybe a mouse. And output, so a television screen or CRT, sound, and maybe some other peripherals. This one is the Amstrad CPC 464 from 1984, and it was powered by a Z80 microprocessor with 64 kilobytes of RAM. Computers like this one were designed to be flexible enough to perform many different types of tasks, not just playing games. And we call a computer system like this one a general purpose computer. Home computers were also mass market products, so street price was a big factor in their design. Another popular home computer of the 1980s was the ZX Spectrum. Here's a close-up of the motherboard. It was powered by a Z80 CPU at 3.5 megahertz, and it had 48 kilobytes of RAM. The CPU is that long chip up in the top right-hand corner. The other long chip over there is some kind of video controller, and the rest of the smaller chips are RAM and ROM chips. The thing to note here is the size of the board, and there's not much to it. Much like home computers of the time, arcade machines also had a CPU, storage, input, so a joystick, some buttons, the coin slots, and output, so a CRT, television screen, maybe a speaker, maybe some of them had flashing lights and stuff like that. Importantly though, they also had custom graphics and sound hardware, kind of like a precursor to modern day video and sound cards. The CPU was typically the same as the ones used in home computers, but the graphics and sound was much more advanced. We call a system like this a special purpose computer. It's designed to run only one program, i.e. the game. These products were not for mass market. Cost was still a bit of an issue, but less so. So for Riga, here's a close-up of the circuit board. This is the topmost board. There's two boards in the system. So it's got two Z80 CPUs running at 4 megahertz. Program ROMs, main RAM. So, the program ROMs are those things with the stickers on them, the colored stickers. Main RAM, audio amplifier, and power conditioning circuitry. On the bottom side, the bottom side's dominated by the graphics hardware and tile ROMs. So those numbered chips in the middle are all the tile ROMs. As you can see from the images, on the hardware level, arcade machines had a lot more going on than home computers of the time. Now this is all very interesting, but how do they actually work? To understand how an arcade machine works down to the finest detail, you've got one of two options. A, you could buy one of these PCBs from somewhere like eBay and attempt to reverse engineer it. Or B, if you're lucky, track down a copy of the original schematic diagrams and try to understand how it works. So I wasn't keen to invest in buying a PCB for this project because I didn't know whether it would pan out at all. So I managed to track down a schematic diagram instead. This is a page from the Riga schematic showing the CPU subsystem. So that rectangle over on the left-hand side, the long one, is the CPU. And that's hooked up to various RAM and ROM chips and other bits of the hardware. And this is actually just one of 10 pages of the schematic. Some of them are available online just through like arcade preservation websites, but others others aren't available actually. So early home computers used to ship with manuals, which often included schematic diagrams for things like repair and modification. But arcade machines were no different, but unfortunately they later stopped producing those schematics when piracy and bootlegging became an issue. So if you sit down and read the schematic diagram, you can see that arcade hardware is roughly split into a number of different subsystems. So we've got the CPU, storage, so RAM and ROM, graphics, which is things like screen drivers, tile maps, sprites, colors, etc. Sound, so that's sound effects and music, and input, that's the joysticks, buttons, coin slots, and dip switches. The most critical part of the entire arcade hardware design is undoubtedly the CPU. Without it, nothing else would function. There would be no graphics, no sound, and no game logic. Its job is fairly simple: fetch instructions from ROM, execute them, and store any changes back to RAM, and importantly, tell the other subsystems what to do. The Zilog Z80 is arguably one of the most successful processors, 8-bit microprocessors of all time. It was widely used in home computers, consumer electronics, embedded systems, and military applications. Its low cost and feature set made it a popular choice for early arcade hardware engineers. It was also used in home game consoles like the Nintendo Game Boy, Sega Master System, Mega Drive, and Game Gear. And it's still actually widely used today. If you own one of those Texas Instruments graphing calculators, they're all powered by Z80s still. It was originally developed in 1976 by Federico Fagan. And over the years, there's been much written about this chip. It had an 8-bit architecture, which means it could read or write a single byte to the data bus at a given time. It had 16-bit memory addressing, which means it could address up to a whopping 64 kilobytes. And because it was so popular, there's actually many open source emulators available today. Interestingly, Rygar uses 2 Z80s, one for the main CPU and one for the sound engine. When I was searching for images of the Z80, I came across this ad and I thought it was slightly ironic. So this ad's from the 1980s and it's pitting the Zilog Z80 against the Intel 8080. But ironically, they were both developed by the same engineer in the mid-1970s. And after he developed the 8080 at Intel, he left that company to create his own startup and produce the Z80. But yeah, this ad was kind of pitting them as the battle of the chips. Arcade hardware contains 2 different types of storage, ROM and RAM. And these memory chips can be many different sizes, but they're often banked together to form larger contiguous blocks of storage. Read-only memory, or ROM, is used for immutable storage by the CPU and other subsystems. It's typically used for things like program data, graphics, tiles, audio samples, and other things like that. In the 70s and 80s, ROM was relatively cheap compared to RAM, which is why arcade hardware tends to be dominated by ROM chips. It has very fast access time when compared to things like disk drives, and that is the time that it takes for the memory device to load the contents of an address and present it on the data bus. It's quite easy to emulate ROM, actually. You can just load the data from a file and store it into a simple byte array. RAM is used for reading and writing by the CPU. It's typically used for storing the results of calculations, lookup tables, graphics buffers, etc. And as I mentioned, it was relatively more expensive than ROM at the time, which is why we see such low RAM capacities in the original hardware designs. These machines use something called static RAM, which is sort of similar to the SD-RAM that we have in our modern-day computers. The main difference is that modern SD-RAM has much larger capacities than SRAM, which was typically only available in the tens of kilobytes. But interestingly, SRAM has much faster access times than SD-RAM due to the way that SD-RAM works internally, which was actually an important factor in these machines. So a Z80 CPU has a 16-bit address space, which means it can reference up to 65,000 odd different memory locations. But given our RAM and ROM storage is spread across multiple different devices, how does the CPU reference them from the same address space? The answer is something called memory mapping, where we basically smush all the different devices together into one contiguous address space. So here we can see the first at the top, we can see the first 32 kilobytes of the address space are mapped to program ROM number 1. And then the next 16 kilobytes to program ROM number 2, then the work RAM, character RAM, and so on. It's worth pointing out that the very last 2 kilobytes of the address space aren't mapped to a memory device at all. Rather, it's mapped to things like the player input states, keyboard buttons, and those kinds of things. This is something called memory mapped I/O, and I'll touch on that a bit later. As we saw from the Rygar PCB, the bulk of the arcade hardware is dedicated to graphics processing. In order to achieve cutting-edge graphics performance of the time, custom hardware was required. Engineers also relied on some pretty clever little tricks to get the most out of the early hardware. One common optimization they made was to allow the CPU and the graphics subsystems to access the RAM at the same time, using something called direct memory access, or DMA. This avoided having to rely on the CPU to move graphics data around so that it was free to do other things. And it was optimizations like this that allowed the engineers to squeeze the most out of the hardware of the time. Arguably, the end of the graphics pipeline is the player looking at an image rendered onto the screen. CRTs, or cathode ray tubes, were widely used for arcade machines. And even today, they're preferred over LCD panels for their authenticity. And I think the authenticity boils down to the appearance of the scan lines that you might be able to see in that image there. And for some emulators, people painstakingly try to replicate the appearance of scan lines using shaders, but there's nothing like the real thing. For those not familiar with how CRT technology works, it literally relies on shooting a beam of electrons at the phosphors in a vacuum tube to produce an image. Deflecting coils on the X and Y axes are precisely controlled to move the electron beam across the screen from left to right, top to bottom. And the left to right motion is called a scan line, and the top to bottom motion is called a retrace. I'm not going to go into a huge amount of detail here, but this is just to give you some appreciation of how a CRT driver circuit works. It has to generate very precise timing signals to position the electron beam on the screen and change its intensity as the picture is rasterized out. And the whole screen gets painted 60 times per second. But thankfully for the emulator, we don't have to worry about a CRT, although I did have to learn about how that worked for the FPGA version. So the graphics you see rendered on the screen are actually split up into 5 distinct layers. In the front, we've got the object layer, which contains sprites for like the player, the enemies, I don't know, power-ups, things like that. Behind that is the character layer, and that's kind of the game chrome, so the high score, any other static information. Then we've got the foreground and background layers. So they contain things like ground, sky, rocks, trees. They're basically the scrolling parts of the screen. And finally, behind all that, not depicted, is the fill layer, which is just a solid color that can be rendered underneath everything else. The character, foreground, and background layers are all actually something called tile maps. To save RAM, tile maps are divided into a grid of 8 by 8 or 16 by 16 tiles. And the foreground and background tile maps can be scrolled vertically or horizontally. And this is to give the illusion to the player that they're moving around in a 2D world. This is another one of the very clever optimizations that the early engineers made. So rather than store the entire bitmap for the foreground layer that you can see on the left there, rather than store all of that in memory, it's broken up into a grid where each cell points to a small piece of bitmap data stored in the tile ROM, which you can see on the right-hand side there. And as I mentioned, these tile bitmaps make up the bulk of the data stored in the ROM chips. Sprites make up most of the moving objects on the screen, and the sprite layer is actually quite different to the way the tile map layer works. Sprites can be positioned arbitrarily, and they can be flipped vertically or horizontally, as opposed to tile maps, which can only render tiles in a fixed grid. Some sprite engines from more advanced machines allowed sprites to be rotated in 2 or 3 dimensions, but that wasn't the case in 1986. And then there's the color palette. This is an example of the color palette that I just rendered out as I was debugging the emulator. So the tile data is stored in the tile ROM chips without any color information, and the actual pixel colors are looked up from the color palette. All of the input for Riga was handled with memory mapped I/O. This is a neat trick which allows the CPU to access the input devices just like regular memory. And the input subsystem consists of things like joysticks, buttons, coin slots, and dip switches. Obviously, we don't physically have any of those things in an emulator, but we need to add them into the VM so that the game knows what to do. So we want to write an emulator, but where do we actually start? And how are we actually going to build this thing? First, we need to decide what is the minimal virtual machine that we need to build to run the program. I chose to hook up the CPU and the memory without much else. We need to identify parts of the arcade hardware that can't or don't need to be emulated, such as the CRT display, or parts of the GPU that are concerned with where the electron beam is on the screen at any one time. We don't have an electron beam. We also don't want to reinvent the wheel. So as much as I would have liked to have learned about every little moving part of the design, when you're on a mission, you need to stay focused. And I kind of know myself well enough to know that if I risked burning out on this project if I kept going down little rabbit holes. I also chose to use open source libraries wherever I could possibly do so. So this diagram shows a high-level overview of how the different parts of the emulator connect together. In the dotted section at the top, that shows the components of the virtual machine, and the things outside of that are just the parts of the application that communicate with the virtual machine. So the VM's got the CPU, which is connected to the RAM and the program ROM. The GPU is connected to the RAM and its own tile ROMs. And the GPU's job is to produce data for the screen buffer, which the application renders to the screen. Player input's captured from the keyboard, and then that's converted into the memory mapped I/O that the CPU reads. And so keeping in line with my mandate for not reinventing the wheel, I decided to use an open source Z80 emulator rather than write my own from scratch. So I landed on this library called Chips, and Chips takes care of the Z80 emulation really nicely, and it also emulates other great 8-bit chips from many arcade machines and game consoles. Importantly, it also includes a memory mapper, which I'll show you a bit later. And it's really nicely tested, written in standard C, and actively developed. Overall, it's just a really nice piece of software, so I ran with this for the CPU emulation. To emulate memory, we just use simple data types for the RAM and ROM. So because the capacities of the RAM and ROM chips on the arcade hardware were so low, you can get away with using static arrays like this. So here we've got an example of a 32 kilobyte CPU ROM up the top with just some hard-coded data, and you can get away with hard-coding the ROM contents. And down the bottom, we've just got some working RAM, 4 kilobytes. And as far as storage goes, there's not much more to it than this. There's nothing stopping you from writing data to the ROM. It's just up to your programming conventions to prevent that from happening. But you don't need anything more fancy than this to emulate memory. The chips library also makes it really easy to define that memory map that I showed you earlier. So here I'm joining the RAM and ROM arrays together to define the entire memory map using a really nice API. So firstly, we define a memory data type, initialize it, and then we start defining those sections of the memory map that I showed you. So up the top, we're connecting the CPU-ROM array to the memory device, and that makes up the first 32 kilobytes. And then the CPU-ROM 2, and so on. And the last two lines there show you the API for reading and writing from that map to memory. So for example, if we want to write to address 1234 with the byte FF, that's how we would do it. And if we want to read it out, the same. And the memory mapping data structure will make sure that that read happens at one of those particular memory devices. The GPU on the original arcade hardware is heavily designed around the CRT timing, but since there's no CRT in the emulator, there's no need to emulate the GPU down to the chip level. The real GPU is concerned mostly, as I said, with the position of the electron beam, and it's heavily optimized around that. So in this case, it's far easier to ignore the hardware here and just try and figure out what it's actually doing. And the most complex part of that was just figuring out how the tile data was decoded and rendered on the screen. So all the graphics pipeline needs to do is produce a composite of the 5 different graphics layers, and it also needs to decode those data structures used for representing tile maps and sprite layers.
Sorry, you're saying that this doesn't
Yeah, in the emulator it does, yeah.
Right, but not on the real hardware.
No, no. The real hardware is like rendered out scan line by scan line at a time. Yeah, yeah, it's pretty crazy how they used to do it. So this diagram shows the pixel pipeline for a tile map layer. So firstly, up the top, we've got the tile code that's read out of the video RAM. And the tile code is used to look up some ROM data from the tile ROMs. And the tile ROM data is actually split up into 3 bit planes. Those bit planes are then combined together with the color value from the color RAM to produce a palette index value. Then the palette index value is used to look up the actual color from the color palette. And finally, you've got the color of your output pixel. Yeah, it took me quite a long time to figure out that stuff from the schematic. Obviously, I could have cheated and looked at other emulators like MAME, but I wanted to figure it out for myself. So finally, we've got to figure out which platform we're going to run this whole thing on. And I landed on a platform called Sokol, which provides some nice C libraries for things like graphics, sound, I/O, and so on. It can produce Linux, Mac, and Windows binaries, and it can also produce web assembly using mscripten, which is a C to WebAssembly backend for the LLVM compiler. And you should definitely check it out if you're interested in compiling your own C or C++ applications for multiple targets. It's a really nice experience. All right, so finally it's time to pray to the demo gods. The first thing I wanted to show you was one of the experiments I did along the road to getting the emulator working and all hooked up properly. Righto, so what's being rendered here on the screen isn't actually output from the graphics pipeline. Here I'm just debugging to dump out the contents of the working RAM. And the reason I wanted to do this is so I could figure out whether I had the CPU hooked up properly to all of the memory chips. And if I didn't, then you would expect to see garbage data here in the working RAM, but it actually looks really structured. And you can even see like things flashing on and off. So that section flashing kind of in the top third of the image is from the character layer. So those are the tile codes I talked about before, which look up pixel data. But yeah, all this stuff seems really sensible. Those are the high scores being displayed, I can tell. It'll make sense later if you see the actual like attract mode of the game. But yeah, you can totally correlate what you see there to the end result of the game. All right, so master. I didn't capture any other experiments on the road with the emulator, so I'll just show you the finished product. So this is booting up and running the totally 100% unmodified ROM data dumped out of the, someone's original arcade machine. Yeah, running in this little virtual machine, which was quite amazing by the time I got to this. Like, there was so much chipping away, but my strategy was basically to do a whole lot of little experiments and then kind of bring them all together. So here I can put some coins in with my virtual buttons and fire up a game. Yeah, and it was quite great to like recreate my favorite game from childhood and get to play it again. And just to show you how show it working in the browser. So, I mean, that's not too exciting. It's literally the exact same thing, but running in the browser. But it was pretty cool that I got that for free just because I used a great little framework. All right. Okay. So finally, I wanted to get onto the real reason that I decided to write an arcade emulator in the first place. And an arcade emulator was just the first step in my strategy to learn as much as I could about how the original arcade hardware worked. The beauty of an emulator is that it teaches you the fundamentals without getting bogged down in the total nitty-gritty of all the chips on the board there. Also, you can recompile it really rapidly. So as you saw, I rebuilt Rygar there in like sub 10 seconds, which is awesome. Because if you want to like tweak things and learn how they work or fix bugs, then it's a really fast development cycle. My original plan was to implement Rygar at the hardware level, down to the chip level on an FPGA. And for those who haven't come across FPGAs before, it's kind of like programming, but instead of writing code that just gets executed sequentially, you're describing a circuit with logic gates. An FPGA allows you to describe these circuits using something called a hardware description language. And there's a few of those. The popular ones are VHDL and Verilog. And the platform that I chose to develop it on is called the TerraSync D10 Nano. And yeah, it's just this little FPGA development board. But there's this great community working on this project called Mister, which is all based around this development board to reproduce all kinds of things like home computers, Commodore Amiga, Atari, Apple, early PCs like 386, 486, and then consoles from Sega, Nintendo, Neo Geo, and a growing list of arcade cores. If you want to check that out, it's got a great wiki and guides on how to get set up. And this board costs about $100 at mr-fpga.org. Importantly also, yeah, this particular board is like a university development board from that company, but the platform that they've built to run on the Cyclone 5 FPGA there is completely open source. So feasibly, if someone built an open hardware design for the same board using a Cyclone 5, we could just port everything to it. So here's some images for how I got started with the FPGA version. I pretty much had to throw away the emulator completely because it doesn't make sense at the hardware level. It was just a learning tool. And so I was back to square one pretty much. So this is me debugging the Z80 CPU, now running on the FPGA. And kind of like the demo I showed you before, I wanted to prove out that the CPU was actually executing real instructions and not just doing some random stuff. And the beauty of FPGAs is that you can do things like slow the clock down. So the original hardware was running the CPU at 4 megahertz, which is like 4 million clock cycles per second. So if you can imagine those LEDs flying past it, I don't know, 2 million times a second changing, it's just this blur of color. But if you slow it right down, then you can actually see the CPU executing instructions. So those pink lights are the address bus, and the other ones are like status bits. So from the assembly of the original game, I was able to see, okay, it's doing a jump instruction here, and so then it would go to another address, and things seemed to make sense. And then I completely threw that thing away and said, right, that was a successful experiment. Now on to the next thing, which was the CRT driver. So I bought, a Sony Trinitron 6-inch CRT and started figuring out how I could actually drive it with electrical signals. So what do you need to do to get RGB picture on the screen? And that was a pretty interesting learning process. But yeah, it turns out all that stuff, that old technology is really well documented, really well understood, and it's quite easy to learn about. And building on that previous experiment, I did another experiment where now that I could render stuff to the screen, I just dumped out the contents of the tile ROMs on the screen so that I could work on the decoding logic, the decoding circuits for that stuff. And that was a bit of a milestone. And so once I had all the tiles, then I could do things like build a sprite engine. So this is like an output from an experiment with my sprite engine where I'm actually rendering those tiles together into sprites that I could move around on the screen independently of each other. And then finally, this was a huge milestone for me. I booted up the working game on the FPGA. So here I hadn't finished the graphics pipeline yet, but you can see it's the working thing. There's some problems with the way it's rendering. It's in black and white, but it's totally running the game. And after I had added colors and fixed up graphics layer priority issues, I had a running game. So everything I learned about the emulator, I was able to translate over to the FPGA, and yeah, I'm soon to release it. Thanks. So what's next? I didn't touch on sound in this talk because that's a whole other bag of hurt. But I kind of skipped over the emulated version of that and just went straight to hardware. So I've already almost completed that for the FPGA. It's just got a few little glitches. But I'll be addressing stuff like that in the coming weeks and months now that I can get back onto this project. It's all been in my spare time, so like Christmas and everything was a bit of a hiatus, but you know, back to it. And there's also a few other games that Tecmo released around the same time. So one's called Silkworm. I don't know, there's about 5 or 6 of them, which have like super similar hardware designs to Rygar, apart from a couple of tweaks. So they're actually really low-hanging pieces of fruit. I should be able to get those games running with very little work. So yeah, there's a few easy wins there. Yeah, so both the emulator and the FPGA core are released under the MIT license. So you can do whatever the hell you want with them if you're interested. I also encourage you to have a read through the code. So I kind of was, when I was doing this, I wasn't just like blindly going down some path, just hacking like mad. I was trying to, you know, write good code, leave comments so that, you know, future me or someone else could come back to it and go, oh, cool, I understand how this works. That was a problem with, I read some source code for other arcade cores and people had kind of just like gone mental and, you know, just hacked away until they got it working. So it was almost impossible to learn anything from it. And I've also blogged a bit while I was doing some of the FPGA work. So there was, you know, more detailed stuff that I kind of went into, like SD-RAM. So I've written some blog posts about that stuff if you're interested. So yeah, check it out, and thank you very much. Any other questions?
What would if you go to FPGA, sorry.
You first.
If you go FPGA route, roughly what was the cost to put all these bits together?
So for FPGA, you actually don't need, like, I just had that board, the Terrasic Nano that I showed you before. The only other thing I needed was a SD-RAM chip. And so around this MR project, people have produced a whole bunch of stuff like cases, RAM chips, other peripherals and stuff that you can just like plug onto that development board. So it was like around $100 for the development board and I don't know, $50 for an SD-RAM chip. And the reason you need an SD-RAM chip is because there's actually like not enough space on the FPGA to store all the original ROM chips. So you have to like, MR actually copies that stuff onto SD-RAM and then it can execute that as though it's a ROM chip. But yeah.
So you mentioned there was no frame buffer back then. Is it because the resolution was so high compared to the computers we had that it just wouldn't fit, it would cost too much in RAM chips?
Pretty much, yeah. The cost is the main thing that I can see there. So Rygar has a frame buffer for the sprites, but for all the other layers, there's nothing. And then the final output is just like pulling a value out of the sprite frame buffer and mixing those pixels with whatever's in you know, the tile maps and the character layers and producing an output pixel for wherever the electron beam is on the screen. And without a frame buffer, you know, there's no RAM chip to just like read what's the value on the top left right now. You have to consult all the different layers of the hardware. And so as it's scanning, it's like reading tiles out of the ROM to anticipate where the electron beam's going to be so it can display it. Yeah, it's quite optimized.
And then the computer version that you wrote, the first one, how different is it from MAME? Or is it similar?
From MAME?
Yeah, or is it just...
Yeah, so I had a look at MAME and, you know, I just couldn't understand it because, you know, it's so generic. It runs thousands of games. And so it's kind of very abstract from how the actual real game works. So it's pretty difficult to go from the schematic and see, this is where that thing's implemented in MAME, which is why I wanted to write my own emulator, basically, just so I had like a nice little version that I could learn from. Yeah. There's one up there.
Presuming one of the peripherals was for the video interface, what was the video interface? Was it VGA or something else? Or,
no.
Or RGB?
Yeah, it was like 4-bit RGB. So they had a manual digital to analog converter. and it was only 4 bits per channel. Yeah. It was quite limited. So they pushed the most out of the hardware at the time.
Any more questions?
Great, thanks a lot.